and the acidity. Let's look at the problem. First, we have a hydrochloric acid, but this one, hydrochloric acid, can be present as a molecular gas phase molecule. When it is dissolved in water, it is acting as a strong acid. So let's look at first, in its gas state, we have a sample of hydrogen chloride gas stored in a rigid 6-liter container at 7.45 atm of pressure and 296 Kelvin of temperature. First, calculate the number of moles of hydrogen chloride gas in the container. So this one is definitely application of ideal gas law. We are given the volume of the container. Let's write the volume of the container, which is 6.00 liters. And the temperature is given, pressure is given 7.45 atm of atmospheric pressure. And the temperature is given as 296 Kelvin. And out of 4 variables, we have pressure, volume, number of moles, and temperature. These are 4 variables that is represented in the ideal gas law. Out of 4, 3 of them are given, and it's asking calculate the number of moles of hydrogen chloride gas in the container. Let's write the equation ideal gas law, PV equals nRT. Here R is equal to 0.08206 liter atm per mole K. So we need to represent pressure in atm unit. If it is given in millimeters of mercury or torr, we need to convert this one into atm first. And volume must be in liters. And moles must be mole, and mostly temperature must be in absolute Kelvin unit. If the temperature is given in Celsius, convert this one to Kelvin by adding 273.15. Okay, we are ready, everything is given. Now let's rearrange the ideal gas law. PV equals nRT. So N is unknown, and let's leave the unknown on one side, everything else to the other side. So let's divide both sides by RT, and we have this equation now. Number of moles calculated by PV over RT. I see the volume is liter, check. The volume is correct, unit is correct. Pressure is atm, unit is correct. Temperature is Kelvin, unit is correct. Then we are ready to plug in everything. So it is 7.45 atm multiplied by volume 6.00 liters and divided by 0.08206, 0.08206 liter atm mole K, and times temperature 296 Kelvin. Then at atmospheric pressure, liter cancels out, Kelvin cancels out. The remaining unit is 1 over mole, which is mole. Which is mole right there. And they simply calculate it, and then with the represent proper number suffix, 3 suffix here. So then let's represent our answer with 3 suffix, and it is 1.84 moles of gas, hydrogen chloride gas, in that 6-liter container. Now let's move up to another problem. Now the rigid 6-liter container of hydrogen chloride gas is cooled to a temperature of 271 Kelvin. What would be the pressure to? Here, let's write the condition. Initially, the pressure was 7.45 atm atmospheric pressure, and volume was 6 liters of volume. Temperature was 296 Kelvin. Okay, in pressure 2 is unknown. It's asking to find the pressure. And volume doesn't change, it is a rigid wall, 6.00 liters. And temperature was cooled to 271 Kelvin. So it is slightly below 0 degrees Celsius. Okay. So in this kind of change, this is a change of state. Always think about combined gas law. P1, V1 over T1 is equal to P2, V2 over T2. And in this case, and V1 and T1, they do not change right there. They do not change. So then let's cancel out V1, V2, because they are the same value. And then the value would be, let me erase this one. Let me erase this one, okay. And our equation is now this equation, P1 over T1 is equal to P2 over T2. So let's multiply T2 on both sides to find P2. Then what we have this one. So T2 cancels out. P2 is equal to P1 times T2 over T1. Okay. So then let's plug in everything we are ready. P2 is equal to P1. P1 is 7.45 atmospheric pressure times 296 Kelvin over, no, T2 is 271. So let me correct it. So it's now 296. It should be 271 Kelvin over 296 Kelvin. And then Kelvin cancels out. It is now 6.82 atm, atmospheric pressure. Now let's take time of evaluation. The pressure has decreased. Does it make sense? Yes, it does, because the temperature decreased. As temperature decreased, kinetic energy decreasing. So evaluate. Okay, so temperature has decreased, and it causes kinetic energy of molecules decreasing as a result. Because it is rigid wall, the volume is the same, and the molecules are moving slower than before, then it's hitting the wall less frequently. As a result, pressure must be decreasing. Initially, it was 7.45 atmospheric pressure. Now it is decreased to 6.82 atm of pressure because of this temperature decrease. This one really makes sense. Now let's move up to the next problem. When hydrogen chloride ionizes in aqueous solution. So when hydrogen chloride gas is dissolved in water, it becomes a strong acid. It is completely ionizing to form hydronium ion and chloride ion. Chloride ions are formed. In the following box, draw 3 water molecules with proper orientation around the chloride ion. So here, water is formed oxygen and hydrogen right there. So water is H2O. Remember, water is much more electronegative than its hydrogen. So water has strong partial negative charge. Oxygen is partial positive charge. Okay, so when you look at the structure of this chloride ion, this is negative charged. And then the positive charge will be facing negative charge, like this way. Positive charge will be facing negative charge. Positive charge will be facing negative charge because same charge will repel. Positive charge. Positive side will be facing same charge repel and different charge attract. So then when water molecule is facing chloride ion, it will be forming hydration, layer of hydration, and hydrogen ion will be facing chloride ion. Now let's look at the C. C is the major problem in this problem. We are given 3 acids, nitrous acid, hydrochloric, and perchloric acid. And its conjugate base anion is given nitrite ion, chloride, and perchlorate ion. Ka value of the acid is given 5.6 times 10 to the negative 4, 2.6 times 10 to the negative 10 to the 7th, 1.6 times 10 to the 15th. The Ka value for 3 acids are shown in the table. Which acid is represented in the diagram? First, let's look at the Ka value. Here, the Ka value is much smaller than 1. And this one, K value is much bigger than 1. 7 order larger than 1. And this again, much bigger than 1. And remember, Ka value is really representing the acidic strength. And the Ka value is, so when Ka is 1, that's for hydronium ion. So hydronium ion, Ka value is exactly 1. Hydronium ion is very strong acid. We are using in aqueous solution, strong acid. And K value is negative, less than 1. This is meaning it is a weak acid. And when Ka value is bigger than 1, they are strong acids. Strong acids are completely ionized in aqueous solution. Okay. And please remember 6 strong acids. What are they? They are hydrochloric acid, hydrobromic acid, hydroiodic acid. In these halogen-like acid, except hydrofluoric acid, they are strong acids. And 3 more, they are oxy acids like nitric acid and sulfuric acid. Finally, these perchloric acid. These are 6 strong acids. Six strong acids. They are completely ionized in aqueous solution. And we can safely assume that all the other acids are weak acids, especially carboxylic acids. Carboxylic acid, you see the example in 2022 and 2024 free response problems. Here now a snapshot, a diagram representing this acid is shown. And here that majority of the acids, they are intact HA molecule as it is. Only small number of these acids are ionized, meaning it is partially ionized. Partially ionized, which is on a weak acid. Weak acid is partially ionized. Most of the molecules will be remaining as intact of HA acid, only small portion. Typically, less than 5% of the molecules will be dissociating to produce its conjugate bases and hydronium ion. So in this case, this is partially ionizing, must be weak acid, and nitrous acid will be the answer. All the other acids, the K value is very large. They're all strong acids. So this one is asking about the concept of a strong acids, and the weak acid is asking us to recognize it. Can you recognize those strong acids and weak acids? And this concept also in combination with the